Chapter 6 is about flip-flops. The first 5 sections of Chapter 6 we're going to cover, and then we're going to have a test along with everything in Chapters 5 and 4. We've been through Chapters 1 through 5 talking about combinatory networks. That's when the inputs hit our circuits and our circuits have energy flowing through them at almost the speed of light. Our outputs then change almost instantaneously. Now what we're going to begin doing is considering two types of inputs. One comes from memory, the others are normal inputs. And together the knowledge of the past plus the present is going to determine our output. So really this chapter is about the various types of memory. This first half is just about these types of memory. The second half of chapter 6 is on applications, and that's where we begin designing circuits to work with this memory. So we're really going to just focus our attention here on this red arrow. Networks that consider both memory and input are called sequential networks. Sometimes they're called finite state machines. We're going to call everything we cover in chapters 6 through 9 a sequential network. That's the remainder of this course. So some of the questions we can ask about this is, how is memory created with NAND gates? And what causes something to be remembered and other things to be ignored? We're going to have two different kinds of answers to this second question. Chapters 6 through 8 are going to use a clock to determine when something's remembered. So we're going to try to run the clock as fast as possible to capture all the events of reality. Chapter 9 goes back to how the brain works. There is no clock, and we use the events of the world to trigger memory. So this is the outline of what we're going to do. We're going to study bistable elements, then flip-flops, the various types of flip-flops, the set, reset, D, JK, and T, toggle. Then we're going to learn some new software because Logisim doesn't really do timing diagrams. It just does those blue circles that we've seen before. And we're going to study master-slave configurations and different kinds of flip-flop triggering. Let's get started. This is my first crack at a bistable element with Logisim. I have, under simulate right here, I have it unchecked so I can single step through it. Blue means Logisim has no clue what's going on. Red means that the same situation's been repeated over and over and over. It can't make up its mind, so therefore there's an error in the circuit. Now this is an error in the simulation. It's not a reflection of what will happen in reality. What will happen in reality is this circuit will be powered on and it will do something. Here's an example of something it might do. So it might go on to the 1-0 state. Now you can see that it's stable. If I press Control-I now, it's stable. It could be stable in another state. Now I have to force it here in Logisim. So you can see how the 0 and the 1 switch positions. So when it powers up, it can be a 0 or a 1 or a 1 or a 0. The only real bistable element that's designed to teeter on the balance between 0 and 1 and 1 and 0 and just oscillate back and forth is called a 555 timer. And that chip, you hang capacitors on it and you can change the rhythm or the frequency that it oscillates in. So it's called cross-coupled because there's a cross right here. So you follow this line, and then you follow this line. You can see there's a cross. That's the cross-coupling. It's also called feedback because this is the first time we're taking our output and then feeding it back into our inputs. This is what creates memory. And it has two stable states. It can be 0, 1 or the opposite, 1, 0. It stays that way until power's removed and powered on again. And then randomly it'll choose one of those states. Just like with a NAND gate, we can build an entire computer with a NOR gate. It's just not normally done. But when understanding these flip-flops, it's actually a little bit easier to start with the NOR gate. So I'm starting off with 2 of these, and we're going to hook up the cross connect or the feedback. Here. Then I'm going to take the output and hang it off the output of each of these NOR gates. Right now it's blue because logicism has no clue as to what to do. Okay, let's look at simulate. Let's enable simulation. Now it says error. Let's see if I can poke it into behavior. Yes. This is called the reset input at the top, and this is called the set input at the bottom. And then this is called the Q output, and then this is called the Q bar because it's typically the opposite, but not always. And it's that behavior of not always that's what's most interesting. Okay, so now I'm going to poke at it. At this point, I've hit the reset button and it's reset. Now I'm going to go to 0 and it remembers until I hit set. When I hit set, this is setting the output as a 1, and then its twin is usually the opposite. So now it's remembering. No matter what the set is, it's remembering the output. If I say reset, now it remembers that. If I say set, now it remembers that. So we're looking at memory for the first time. And this doesn't have to be done with electronics. It's done with air pressure inside of a jet engine. It's done with mechanical objects. That's why a mechanical computer can be built. The one thing where these stop being the opposite of each other is when we both, in this NOR gate world, is when we set them both as a 1. When they're both at a 1, both the outputs are zeros. This is not bad in and of itself. No circuitry is going to burn up. But the next question is, what happens if we go back to a 0 right here? Well, then it sets. What happens if we go back to a reset? Well, it resets. And in the real world, you cannot change both of these at the same time. You can only have 1 bit changing on the input at a time. But if we simulate a clock, so we have to turn the simulation off and put these both at a 1, and let's let it percolate through and get to the 0 state. Okay, now if I set these both at 0, Logisim's going to have no idea what's going on because it can't change them both to 0 at the same time. I've changed them both to 0 because I've turned off the simulation. I'm single stepping it. So I made 2 changes in this fake world, and now I'm going to press Control-I, and we're going to watch it oscillate. Wow, look at that. Logisim's oscillating right there. 0011, 0011. I was hoping that it was going to go red. Okay, so I did a quick search on the internet. And if I go up here to project and I say options, then what it does is it says iterations until oscillation on 1000. So basically I'd have to bounce back and forth between here 1000 times and then it should go red. Or what I can do is I can just say go do 1000 times yourself here. Yeah, oscillation apparent. Cool. All right. So let's go back and reset the simulation and press Control-I. Now we're going to an error state. So let me try to poke it into submission and say simulate. All right, there we go, good. So now let's go to that evil 1-1 state, and simulation's enabled. Now I can't actually go and recreate this unless I disable the simulation, because if I press 0 here, if I poke 0, right? It just resets or sets. So in order to recreate the problem, what I have to do is uncheck this and then check these two and then press Control I to get it to oscillate. Now there's another option here. Let's look at this, I think. Add noise to component delays. Let's see if this changes the circuit in any way. All right. So now I'm going to press Control I. And now it's just totally doing random stuff. Isn't this cool? So the real question is, what's evil here? The real question is, what's evil? Set, that's going to work, right? That's stable. Reset, Control I, that's stable. So reset and set both work. And now if I change them both to a 1, this is the evil state, supposedly, right? Both the outputs are 0 now. That's what's strange. But if I change them both to 0, we see the total chaos. All right. Okay, so here we see a summary of that playing around I did in Latches. Here's our NOR gates. Here's our reset. Here's our set. Here's the truth table. When both are 0, it remembers the previous state. So this is the remembering row. This is the remembering state. The next Q is going to be the same as the current Q. The next Q bar is going to be the same as the current Q bar. So this is the remembering state. Think of a row now as a state, where everything's steady out here, predictable. This is the reset row. Reset forces whatever Q was, it forces it to be 0 and forces Q bar to be a 1. So the next Q is going to be a 0 and the next Q bar is going to be a 1. Set forces Q to be a 1 no matter what, and Q bar to be a 0. And when they're both 1, we saw the outputs go to 0, 0. And this by itself is not bad. It doesn't cause unpredictable behavior. It's quite predictable. You set S to 1 and R to 1, then the output will be 0, 0. What's unpredictable is if we change both S and R at the same time with the simulation disabled and single step it, then we get the oscillation because the simulator inside of Latches doesn't know whether you're going to change S to a 0 first and actually reset, or you change R to a 0 first and actually set. That's what's crazy. So this state in of itself is not crazy. And it's not crazy if the next state is this one, the set state. It's not crazy if the next state is the reset state. It's only crazy if you go from 0, 0 to remembering. Okay, so here's the way to think about this entire course. If you want to summarize one intuitive, logical thing that implies all other chaos in this course, this is it. 1 bit at a time. Our chaos is caused by being here and trying to change 2 inputs simultaneously, trying to go from this row to exactly that row. That's the chaos. Now here's a good path. We could go from here to here to here. and everything would be fine. We would end up with a 1, 0 being remembered. We could go from here to this row, and everything would be fine, because we would get a 0, 1 to remember. But when we go from 1, 1 to 0, 0, we have to travel either this path or we have to travel this path. And the simulator doesn't know what's going to happen. And in real life, when you build this circuit, you don't know what's going to happen because it's going to be the non-ideal characteristics of the transistors and capacitors and resistors that this circuit's built out of that are going to determine whether you travel the red or the blue path from this 1, 1 to the 0, 0. But even deeper than that, what we're dealing with is the concept of infinity and infinitesimals. Can you bang on the table simultaneously with two hands? No. There's an infinitesimal difference no matter what. And we're dealing with the speed of light here. So the speed of light is the speed at which energy is moving through our NOR gates or our NAND gates in this memory circuit. And you have to remember that we can't get rid of the infinitesimal. There has to be just one bit changing at a time. I'm editing inside of Camtasia, and I wanted to show you where I banged on the table and see if I can detect the two hands hitting the table separately or it's blurred into one. So I think it's right about where that spike is right there. And what I'm going to do is expand it out as deep as I can. So I'm moving the slider right here, trying to keep it in. Ooh, look at that. I can see it. Look at that. Yes. Now, keep in mind, I was trying to hit the table with two hands simultaneously. You can see the separation between the two, even inside this video editor. Awesome. So our circuit symbol for this is going to be this or this. So you can see the R and the S are flipped positions. This way, when we set, Q becomes a 1. And when we reset, Q bar becomes a 1. And then we can say Q bar, or we can put a little not symbol out here on the end. So let's look at this from a Logisim point of view. Let's just see if we can turn this into NAND gates. So we're going to analyze the circuit. It's computing the truth table. And we see here in the truth table, Logisim is going, and this is remembering, right? This is our remembering right here, remembering state. It's going, I don't know. I don't know exactly what's going on right here. So this is at the point where we have to start thinking a little bit differently about Logisim. It can't do everything for us. But okay, so let's see, what's the expression for it? Not R. That's what it's coming up with. Build a circuit, right? Use and NAND gates. Yes. Well, is that going to work? Let's turn the simulation on. It just does the opposite. No, this isn't going to work. Okay, so we can't use our normal tricks to see inside of a flip-flop. Let's look at this from the point of view of Logisim's actual SR flip-flop. And you can see here there's this memory section, and here's this SR flip-flop we're looking at. So again, let's hook up our set and hook up our reset and hook up our two outputs and look at its behavior. Okay, our goal is to get this flip-flop to behave like the flip-flop we built out of NOR gates. So the closest approximation we can get is where I make this high level, and I go into the wiring, and I pull out this constant and tie the clock input high. Now this will work. So if I go to a set, it sets, remembers, resets, and remembers. The difficulty is when I go to 1, 1. it doesn't display the crazy behavior of our NOR gate. It's been fixed. And to discover how it's fixed, we can see that it's taking on a value and remembering it. So it's acting like a memory state, a remembering state. So I looked up the SR flip-flop truth table in the Latches documentation, and you can see 0, 0 is Q. They're not putting in the Q bar. 0, 1 is 0, 1, 0, 1 is a 1. But here in the 1, 1 column, what they did is put question marks, and that's where you're getting the remembering behavior. So in summary, we don't really ever build flip-flops out of these NOR gates or NAND gates. Even inside the FPGA, there's going to be special circuitry that doesn't look like this, that's going to try to minimize the craziness of the SR flip-flop. Now, when we go to the other types of flip-flops, you're going to see that they solve this problem in different ways than Latches putting question marks right here. But even more interesting, what's going to happen is we're going to start adding feedback. We're going to take this Q and feed it back into the inputs. So we're going to add memory on top of memory. This is when it gets really exciting.